In this video, we're going to show you how you can go in the other direction, so to speak, and use the empirical rule to estimate the standard deviation of a distribution based on a histogram. So the example is going to be based on the diagram that you can see on the screen in front of you right here, and it's sort of unfortunate the way that this is typeset on the page, because for the purpose of this video we have to kind of alternate between the instructions and the picture. So you can see the picture on the screen in front of you right now, and let's take a look at the instructions. So the instructions are visible here for number 16, and it reads, match the histograms in the next column to the summary statistics given. So in other words, they want you to notice you have this table with these summary statistics, and there's some similarities. For example, 3 of the distributions have a mean of 53. So you obviously are not going to be able to match them on the basis of the mean. And if you start to look carefully at what differs, it's the standard deviation that differs. And so the gist of this particular problem is that you can use the empirical rule in a reverse manner, so to speak, to estimate the standard deviation of a distribution when you have the histogram like this. So before we showcase, let's take a quick look again at the empirical rule to see what it says. So if you look at this diagram here, this figure 13, in a way which is going to help with this particular example, what we want you to notice is that you have approximately 6 standard deviations that cover the span of a bell-shaped distribution. So in other words, if you go down 3 standard deviations from the mean and you go up 3 standard deviations from the mean, in other words, for a total of 6 standard deviations, that pretty much is going to cover almost 100% of the data in a bell-shaped distribution. And so we're going to use that as follows. Notice the first distribution, the one that's labeled with letter A. The first thing you have to get is, what is the range of that distribution? In other words, from the lower limit of the first class to the upper limit of the last class, how far is it? Well, if you look carefully at the distribution, you'll notice that the class width is 5. They have deliberately blurred or removed some of the hash marks, not only for clarity, but also to make you think. And so you'll notice that the distance, for example, from 82 to 72 is 10 units, and that covers 2 classes. And so if you take 10 units and you divide it by 2 classes, that tells you that the class width is 5. So for this particular distribution, 32 minus 5 would take you down to 27 for the first class. And so the range here goes from 27 to 82. And so in other words, 6 standard deviations, because it is approximately bell-shaped, 6 standard deviations is going to go from 27 to 82. So we can use that to estimate what the standard deviation is. Here's what I'm saying. When you look at a data set that's represented as a histogram, you can see roughly what the lower limit and what the upper limit are. And so if you take the upper minus the lower and you divide that by 6, that's going to give you a ballpark estimate of your standard deviation. And so for the distribution pictured in part A of the figure, as we said, the range is going to be from a high of 82 to a low of 27. And so if you take the difference, 82 minus 27, and divide it by 6, that's going to give you an estimate of your standard deviation. Let's see what it is. Here we are at the calculator, and so we'll take 82 minus 27 and divide that by 6. And so we're getting 9 and some change. So let's put that down. So for the purposes of this problem, we don't have to be ultra accurate, because we understand that we're not getting the full picture of the data set. We're seeing a representation of it that obscures some of the crucial detail. So I would say, well, I would take 9.16 and I would round that to 9.2, and that would be sufficient. Let's go back and look at the table and see if we can come up with a match for that. Now you have to understand that the standard deviation that's shown here in this table is calculated on the actual data. It's not calculated off of the histogram like we're doing. And so we can't expect it's going to match our answer exactly. We're trying to get in the ballpark and get as close as possible. And so I'm looking here, and I notice that two of the distributions are definitely in the running. One of them has a standard deviation of 10, and the other one has a standard deviation of 11. And so I can't rule either one of those out just yet. I have to go back and take a look and see which one is going to best correspond to letter A. And so I'm looking carefully here at letter A, and as far as the mean is concerned, I would say that the mean for letter A is somewhere between 52 and 57. And so in other words, it's contained inside that tallest bar of the histogram. And so that being the case, having a mean of 60 really isn't reasonable. And I would say that letter A has to correspond to a mean of 53 and a standard deviation of 10 as calculated. Now we estimated the standard deviation as 9 and some change, and so that's close enough. Let's take a look at letter B. Now in letter B, we have a different class width here. So again, you'll notice that some of the hash marks are not labeled, but 2 classes covers a distance of 2 units. And so that would suggest that we're looking at a class width of 1 for the distribution that's pictured in letter B. And that being the case, that would tell us that the range goes from 47 on the low end to 57 on the high end. And so we can then use that to estimate our standard deviation. So I put down the details of my calculation, as you can see, and let's get that number on the calculator. So we're taking 57 minus 47 divided by 6, and that's giving us a value of 1.6 repeating. So let's put that down. So again, I'm not using the conventional rounding rules here because we are estimating, but I am estimating the standard deviation to be around 1.7 after rounding. And so if we go back and take a look at the text, it looks like letter A matches to Roman numeral 3, and it looks like letter B matches to Roman numeral 1. So let's put that down. And so now I'm ready to move on to the figure C in the graph there. Figure C, it's approximately bell-shaped, and again, class width looks like it would be around 10. If you look at the distance between the labeled hash marks, for example, from 103 to 123, that's a distance of 20 units, and it covers 2 classes. And so 20 divided by 2 would be 10, and so that would suggest that the class width here is 10. And that means on the low end, we're starting at a lower limit of 13, and on the high end, we're going up to a limit of 123 on the right side of the class. And so as far as our range is concerned, you can see we have 123 minus 13 divided by 6. We want to get that on the calculator. I have 123 minus 13 divided by 6, and that's giving me 18.3 repeating. So again, I would want to put that down. And so I'm reporting that value as 18.3. And if we go back to the table and take a look at which one that would be, and very briefly notice, when you look at the histogram for letter C, you have 2 bars that are of equal height. One of them goes from 43 to 53, and one goes from 53 to 63. And so on a casual inspection, you might think, well, you know, the mean's going to be somewhere in there. And I would agree, it probably is. But this distribution looks like it's also skewed slightly to the right. I mean, it's approximately bell-shaped. And so if you ask me to pick which of those 2 identically tall bars contains the mean, I'm thinking, well, you know, it looks like it's got to be about halfway in between those there, because we do have quite a bit of mass below 53, but when you have a tail, that pulls the mean in the same direction. And so in this case, I would expect the mean to be pulled somewhat to the right. And so let's take a look at the table and see what we have. Now, on the basis of standard deviation, The only one that's in the running would be Roman numeral 4, because it has the highest standard deviation that we've found so far. And, obviously 18 is a lot closer to 22 than it is to any of the other values. And so I'm going to go with Roman numeral 4 for that, and that would suggest then by a process of elimination that letter D would correspond to Roman numeral 2. Now, of course, you could also verify that in the same way that we've done the other 3, but I think that's sufficient for this particular video. You can take a look and see that it matches. Anyway, hope this has been helpful, and if you have any questions about this, please feel free, drop me a line. Otherwise, go on to the next video.